I want to calculate the kinetic energy of in the case of rotational motion. First of all, let's take we have this object. We have a pure rotation. So in the case of pure rotation, what I mean, we have the x-axis, a fixed axis at the midpoint. In this case, we talked about the velocity of any point. You have v cm equals to 0, and we have v of any point on the object. Let's say va equals to ra times omega at that time t. For example, I take a small element. We have this small element, the element a. During the rotation, we have a trajectory. The velocity of this object, if we have a clockwise rotation, here we have omega at the time t, okay? So the velocity must be tangent to the trajectory like this. This one is VA with a radius equals to RA. The total one equals to capital R. So VA equals to R omega, okay? What about the kinetic energy of this element or of the total object, okay? The kinetic energy of the element A equals to half mVA square, okay? Equals to, you know, V equals to R omega, we can put M over 2 times RA omega square. We get finally kinetic energy of A equals to M over 2 times R square omega square. Okay, I ask you, what about the moment of inertia of the element A? You know, I take a small element of the total object. We have a disk and a small element turns about the axis. What about I? You know, I equals to I cm of the point A plus the mass. Here I take the mass of A, the mass of the element A times d square. Here, you know, the axis is not passing through the point A, the element A, the small mass A. This one has a mass MA. The axis is here. So we can say directly ICM ICM equals to 0 because the axis is not passing doesn't pass through the element A. So here we can eliminate ICM, and d is the distance between the axis and the mass equals to RA, okay, d. So we can say I A equals to MA times RA square, okay. So here we can say kinetic energy of the element A equals to ma r square omega square divided by 2. Ma r square equals to I. So directly we can write kinetic energy equals to I over 2 omega square. So this is the rotational kinetic energy, and you have the linear kinetic energy have mv square, okay? Like this, we can use the kinetic energy directly in the case of pure rotation. Be careful, I take the case of pure rotation. Let's take now the case of a pure translation, okay? In the case of pure translation, the second case, in this case, we talked about this point. Any point of the system is moving with the same velocity like VCM. Here we have V, here we have V, and here we have V. Let's take a small element here, for example. This element also has the same V. All they have the same velocity like VCM, okay? So in this case, we can say the kinetic energy of all the ball, the whole system, equals to half mv square. We can say VCM. M is the mass of the total system of the ball, okay? Here we have capital M. And here we have only translational kinetic energy. We don't have rotational kinetic energy. Kinetic of the ball, we don't have I because we don't have omega. We have only translation, okay? If I want to calculate the element A, kinetic of the element A, we can say kinetic energy of the element A equals to m of A divided by 2 times VA square. We have only translation. We don't have a relation with omega. We don't have omega. Let's take the last case if we have rotation and translation. For example, I take this example. With this example, as you see here, we have a translation from this point to this point. In this case, we have a, without sliding, we have a rotation, the system is rolling around, and we have translation in the same time. We talked about VCM before. We calculate its value equals to R times omega. And also we calculate the value of this point. Anyway, we can use directly. In this case, we have two kinds of kinetic energy. Here we have a combination of translation plus rotation. In this case, we can say the kinetic energy of the ball, of the total ball, equals to the rotational kinetic energy half I omega square plus the translational kinetic energy. Here, be careful. We have ICM. So we can say directly equals to ICM over 2. Here we have omega square plus half m v cm square. Okay, you know ICM of a ball is it's a given value equals to 2 over 5 m r square. R is the radius, m is the mass of the ball, and 2 over 5. And also you know v cm equals to r omega. R omega. Okay, we can do some application about this point to understand very well the situation.